I would like to invite everyone and thank you for coming to this session. And we have our first speaker who has written the book, and many of you are writing, using this for the class. And he's our own from SIMI-ODE. And Dr. Bryan Winkle, he likes him very much. So I would like to invite him to speak. And the session is for 25 minutes. And then after that, we will have 5 minutes break. And I will ask him to finish his talk in 20 minutes. So 5 minutes will be there to discuss or to question.
Okay.
Thank you.
All right. I'm going to share my screen here. And I need to, the host has to enable screen sharing.
So math department, please.
Give me one moment.
Okay, maybe you can go ahead. Check if you can. I did it.
Oh, you did? Okay, let me try
Yeah.
again.
Mhm.
And there we go. All right, let's see. I'm going to go here. So what I want to talk about is a project that, it's a SIMI-ODE project that Bryan Winkle did. And let me put this on full screen mode. It's a SIMI-ODE project that Bryan Winkle made up, and I have used this in class a number of times to introduce, well, to put a new spin on a common DE model. So here's the situation. An object of mass m, you drop it from some height near the Earth's surface, and it falls under the influence of gravitational acceleration. As it falls, it experiences a force due to air resistance, and that's what we want to model, the force of air resistance. Of course, that force should oppose the motion and depend on the velocity of the object. And I'm going to fix the convention that down is the positive direction, so gravity will be taken as positive, and I'll use minus F naught of V, soon to become F of V, as the air resistance force. So that's a function that should depend on V. It should oppose the direction of the object's motion. We're only going to be concerned with downward motion anyway, so a little simple F equals ma modeling that I always do in class. By the time I've done this project, I've done it a number of times, leads you to that differential equation in red at the bottom. V prime equals G minus F of V of T, where F is going to embody the force due to air resistance. And of course, it's a subject of endless debate. What's the proper model for air resistance? Well, the answer is it depends. There are many models for how air resistance affects an object. And a few of them that I like to examine in class is, number one, no air resistance whatsoever. So just take F to be 0. The next easiest thing to do is to take air resistance to be proportional to the object's velocity, where K is going to be some positive constant. I had a minus sign in front of my F in the DE, so it's going to oppose the object's motion. Linear air resistance. There's the traditional pure quadratic air resistance model. You can also posit a more general quadratic model for air resistance, where you've got two terms in there, a linear and a quadratic term blended for some positive constants, K1 and K2. And you can also contemplate a general kind of power law resistance, where K times V to the rth power. And again, V is going to be positive for us, so there's no ambiguity with V to the rth power. So there's 5 models, and it's interesting to contemplate which one is appropriate. Well, that may very well depend on the situation. So I have some data. This is data that Bryan Winkle got. It concerns the fall of a shuttlecock, which is the projectile used in badminton. There's a picture of some. And here's the data. This comes from an article in the American Journal of Physics from 1980. And what the authors did is they dropped a shuttlecock from some considerable height and measured its fall as a function of distance and time. And they have these time distance pairs here, time in seconds and distance in meters. It falls a total of 9.5 meters in 1.873 seconds during the course of this little experiment. And so we want to use that data to evaluate those 5 models and see how good are they. Well, the models themselves come with certain unspecified coefficients in them that are going to depend on things like the shape of the shuttlecock, the density of air, that sort of thing. Okay, that we need to figure out, first of all, what parameters should we use in each of those 5 models that will yield a solution to the differential equation, the motion of the shuttlecock, that best fits the given data. So the general procedure, which I will illustrate with one of those models, goes like this. Solve the ODE, whichever model you're interested in, solve that ODE. Conceivably, do it, if possible, do it symbolically with the parameters, the unknown parameters, those constants, K1, K2, whatever. Leave those undetermined so you can get the velocity of the shuttlecock as a function of time and as a function of the unknown parameters that you want to estimate and fit to the data. Of course, you compute the velocity, then you have to compute the position by integrating the velocity over time, but that's another step in the computation. But once you've got a prediction of the shuttlecock's position for any given model, adjust the parameters, the unknown parameters in that, to obtain the best possible fit to the data. And this is, of course, is where I get the students thinking about what does best mean. And then once you've done this for each of the 5 models, you find the best fit to the data. Examine each model and decide which one does the best job at describing the fall of the shuttlecock. So let me illustrate this with the linear air resistance model. And of course, like I said, it raises the question of what's the best parameters in any given model? What's the best model? So here's in red there, you see the differential equation that governs the linear air resistance model. You can solve that. That's an easy one to solve. You write out the solution. There it is, assuming that you drop the thing from rest at time 0. Integrate again in time, assuming that the thing starts at position 0 at time 0. And in red there, you get the position, the distance fallen by the shuttlecock as a function of time. It has that unknown parameter K in it. And so I treat X as a function of T and K for convenience. G, at the location that the experiment was conducted in, I believe it was New Haven, Connecticut, they measured G as 9.80136, as many sig figs as you care to believe. So we're going to consider G as a known quantity. So the goal is adjust K in that model for X of T comma K, adjust K to get the best possible fit to the data. We have data, we have 18 data pairs, times, I label the times T0 through T17, the corresponding X positions in meters, X0 through X17. And the goal is this: choose K so that X drills the first data point and the second data point and the third data point and the fourth, up to 17 data points. You've got one parameter, K, and your goal is to make it satisfy 17 different equations. That's going to be that's a long shot. This is, of course, where I raise this issue to the students. And then I lead them gently, if we haven't already done it, I lead them gently to the idea of doing a least squares fit to the data, which some may be familiar with, some of the students. 17 equations and one unknown, no solution. So we're going to try to find a K that does the best job possible at satisfying all the equations simultaneously. Take the 17 equations and write them out in their full glory. There they are at the top of the screen. Write them all. You can take each equation and square the left-hand side and ask that left-hand side be 0. So you see in red there, I would like that relation to hold for each of the 7. Well, the first data point we get by default 0, 0 by construction. But the other 17 data points, I would like to adjust K to make that equation displayed in red there satisfied for I equals 1 to 17. This is essentially a reformulation of make one parameter fit 17 different data points. So then, you can have students debate about what's the best compromise. Well, one obvious thing is you would love to make all those equations satisfied. Instead, settle for minimizing the sum of the squares on the left-hand side here. Try to make all of them close to 0 as simultaneously if you can. If you could make this SS of K, the sum of squares with respect to K, if you could make this function SS of K equal to 0 for some choice of K, you would have solved all 17 equations simultaneously. It's not going to happen. So you opt to minimize that function of K, and this is a way to find a compromise solution. If you plot that function, of course, our students have Maple running on their laptop computer so they can bring it, say we can do this in class. I have them plot SS of K, and there it is. The best value of K for this model is the one that minimizes that function. So this is an easy Calc 1 exercise. You solve it probably numerically, and the best value of K here is about 1.06. It doesn't make SS of K 0. It makes it about 0.52. So that's 0.52 is the residual sum of squares. So for the linear air resistance model, we have found in some defensible way the best choice for K to best fit the data. And the result is, if you plot the linear air resistance model's predicted distance fallen as a function of time and overlay it on the data, you get what you see there. It's not perfect. But it's the best in this sense, the best in the sense of least squares. You can see it's predicting that you fall a little bit too far as you go farther in time, and it's a little undershooting earlier than that, but it does the best it can do. You can do the same exact thing with all the other models. Now, some of the models have only one parameter, some have two parameters. That's a natural Calc 3 multivariable optimization. These optimizations can be done with writing out the normal equations that they have, the partials to 0, or in most software, there's built-in optimization routines that they can use. In any case, you could do this for each of the models, compute the best fit, and then look at the residual sum of squares. How close is it to a perfect fit to the data? Well, here's what happens. With the no air resistance model, there are no parameters to fit. You're just given, the solution is 1/2 GT squared for the distance fallen. The residual is pretty big. I'll show you a graph of how that fits this data. No parameter. You could treat G as a parameter to fit gravitational acceleration, but in general, if you can measure something directly and accurately, do not try to fit it from data. That's one of the lessons I impart to them. The linear air resistance model we just did. The pure quadratic model estimates the constant K 0.212 for whatever that's worth. And it has a residual that's about 50 times smaller than the linear model. So that's dramatically better. If you fit the general quadratic resistance under the constraint that both K1 and K2 have to be non-negative, it chooses the pure quadratic model. It says set K1 to 0. It might want to push K1 into negative territory, but that's a constraint. Keep K1 0, set K2 equal to the pure quadratic model, same residual, but you got that with two parameters. And then you can do the general power law resistance. And surprisingly, it's bloody close to pure quadratic. Not quite. It wants to take 2.02 as the optimal exponent, and K is close to the pure quadratic. It has just a smidgen smaller residual than the quadratic model. So of course, here are 5 models. Here are the plots. There are only 4 plots here because the pure quadratic and the mixed quadratic gave the same result. So those are both in the lower left here. Here's what you get if you on the upper left is no air resistance. That's clearly a loser. Linear air resistance in the upper right, pretty decent fit. Pure quadratic and mixed quadratic in the lower left. That really kind of drills all the data. I mean, not perfectly, obviously, but it's visually indistinguishable. And of course, the general power law fit is also almost the quadratic model anyway, just very, very small differences. So you look at these models and you say, which one should I pick? Which one's the best model for a falling shuttlecock? Well, the first thing you notice is the no air resistance model is just a clear loser. So I would immediately throw that out. And of course, the question is now, which model is best? Models with more parameters almost invariably do a better job at fitting the data, but they're more complicated. Should we, well, I already talked about this. Should we throw gravity into the mix? And the answer is probably not if you could just measure it. But the issue now becomes, would a more complex model that has more parameters, is that a superior choice? I mean, it might give a slightly smaller residual. Well, as I said, no air resistance is terrible. And there's a general principle just in mathematical modeling. If two models give the same result, the model that has fewer parameters is generally preferable. It's a simpler model. And in this case, the linear model and the pure quadratic model both had one unspecified parameter, but the quadratic model gives a much, much better result. That alone would be grounds for throwing the linear model out and going with quadratic. It achieves a much better fit to the data with no greater complexity. And so that's exactly what I just said here. Between the linear and pure quadratic, go with the pure quadratic. But if the remaining models, it's a slightly more subtle question. Of the remaining models, the pure quadratic, the mixed quadratic, and the general power law, which one is optimal? Well, this falls into an area of, well, it's kind of an area of statistics. I call it model selection. And so, and I should tell you a disclaimer here. Sometimes I present this to students, the so-called Akaike information criteria, or AIC. It's a way to examine models and attempt to decide which model is the best model. And what it does is balance fidelity to the data and the number of parameters, and it penalizes models that require a lot of parameters to fit the data. Now, this is a criteria. I'll show you. It comes out of statistics and information theory. I always have some trepidation about showing students a statistical test without a thorough examination of the underlying assumptions, because it's like you're sort of handing them a loaded gun. You got to be careful because they'll misuse it. But I like to bring up the idea that people have considered that the fact models with more parameters are not necessarily better, even if they achieve a lower residual. And people have considered this problem and tried to quantify what the best model is. So the AIC computes the following quantity. P is the number of parameters in your model. N is the number of data points you have. RSS is the residual sum of squares. You compute this quantity, and this quantity, it comes from ideas in information theory and statistics. It's an attempt to decide which model does the best job of explaining the data. I'll just leave it like that. We can compute this for each of the models at hand. Now, it does come with certain assumptions that should be tested, namely that the residuals in your model are independent and in this case, normally distributed, although it can be adapted to other situations. But I show this to the students, and then we compute the AIC statistic for our models. As I said here, there are certain statistical assumptions that underlie it. And in this case, we already threw out the no air resistance model and linear air resistance model. And even if you left them in contention, they violate the statistical assumptions. A quick check shows that they don't really fit the test. But of the remaining models, you want the one that minimizes the AIC. And in this case, that is the pure quadratic model. It attains essentially the same residual sum of squares as the other two models. It does as good a job as them at explaining the data, but it does it with only one parameter. The other two models require two parameters each, and the AIC penalizes more parameters. And so the pure quadratic model would be superior in this case, unless you have some other information. So I use this idea of the shuttlecock fall to make an interesting spin on a common thing that we all do in DE, at least around here, is model a falling body. Do you want linear air resistance? You want quadratic? You want something more general? And I leads them into the idea of least squares fitting to the data, and the idea that more parameters in a model are not necessarily better. This is an idea that comes up in machine learning as well. If you have a sufficiently complicated scheme, you can fit any data set at hand, but it doesn't mean it's going to do a good job at explaining data that you didn't include in your so-called training of the machine. And the AIC is one method for balancing fidelity to the data with a number of parameters. But again, I use it as an excuse to tell students that are interested in mathematical modeling and applied mathematics and data that they should take a statistics course. So that's all I have to say.
So thank you for finishing it on time. It's on time.
Yeah.
So any questions from the audience? Please.
Have you looked at, so a shuttlecock is fairly, the structure and shape is different from, say, like a cannonball or a
Yeah,
baseball, something
yeah.
like that.
Yeah.
So have you ever done other objects just out of curiosity?
I have not. That data was collected by some people at, I forgot where they.
Yeah, okay. So
Yeah.
have you come across any other?
Oh, I haven't, I haven't really looked that hard. I'm sure there's data out there. I'm sure it's such a common thing to do. It would be
Yeah.
fun to, it'd be fun to set up an experiment and do that. I mean, if you look at their data, it fell at least 9.5 meters. So they had some substantial apparatus to
drop
track
it.
Yeah. I think Bryan Winkle does something with coffee filters or something, falling coffee filters, and timing how long they take to fall. It wouldn't necessarily, I don't think it would, data as good as what I've got here would be hard to come by, but cruder data might not be, like take objects and drop them from a fixed height and time it.
Mhm.
I don't know, but I don't have any other data other than that.
Okay.
Yeah.
So that's a very good question. Like you can think of a parachute when they are falling.
Yeah. Yeah. I mean, it's a subject of, I know a guy named Chuck Grutch, who used to be at U of Cincinnati, and he did a lot with air resistance models. He had a lot of data on what's the proper model for air resistance. And his was even more complicated. This was back in the 90s. He published some stuff, I think it was in the College Math Journal, on two-dimensional motion and how do you model the two-dimensional motion of an object undergoing air resistance. That's somewhat more complicated since now velocity becomes a true vector. I looked at that stuff once, but I haven't thought about it for 20 years. So that would be worth investigating if anybody wants something even more complicated.
More questions?
I don't know how if you just jump in or raise your hand.
Go ahead.
So do you ever discuss like errors in the data?
You mean bona fide errors as in outlier type stuff?
Well, yeah, well, I think it's probably not an outlier, but if you look at the scatter plot, it seems like there's a slight change in concavity at, toward the beginning.
You mean like errors as in systematic errors in like that were due to the lack of fit of the model or something?
No, I meant like experimental errors.
Oh,
things from a mismeasurement.
Well, the answer to all of the above is no. I haven't done much with that. I have them when you apply a statistical test, so many statistical tests say the residuals should be independent IID. They should have, maybe sometimes they should be normal. It depends. I have them plot the residuals and look and say, is there a clear trend here? If so, a statistical test is going to be problematic. And if it passes, say like a normality test, like on the data I showed you, the three models that I applied AIC to, the residuals pass a normality test. So that gives you confidence that you can apply the statistical test meaningfully. The other two, if you look at the linear air resistance model, if you look at the residuals there, obviously those aren't in some sense there's no statistics there because there's no parameters to fit. But if you look at like the linear model, I'm sorry, this is the no air resistance. The linear model, it's clearly not. The residuals are clearly not independent random variables. There's an obvious trend to them. The residuals are positive for a while and then they're all negative. So I have them do stuff like that to validate whether a statistical test should be used.
So one more question from Bryan, please go ahead.
Yes, thank you. I was actually wondering what kind of software do you use for all the computations?
We use Maple in the classroom, but I did if on the Semiode book website, I posted code for this, and basically every piece of code I posted to that website, including for this, comes in Maple, Mathematica, MATLAB, and Sage. I just wrote the code cycling through Mathematica, Maple, MATLAB, Sage, Mathematica, Maple, MATLAB, Sage, which made it a hell of a time keeping track of syntax when I was.
Yeah, I can imagine. I can imagine. I actually used your book last year for a course on mathematical modeling, and I loved it, really. I
Oh, good, thanks.
really enjoyed the project. I actually implemented a lot of the projects in R.
Okay,
In our
okay,
studio, in Markdown documents.
okay.
And I was planning to actually share some of them to post them on Semiote.
Good, good.
And
That's
maybe
one
in
of the
Python
questions.
later.
That's one of the questions I have in the textbook session is, are there other languages that would be good to put code, put code on the website in?
Yeah, I mean, I found it very sort of convenient with Markdown documents because you can combine code, text narrative, LaTeX, and just produce publication quality project reports.
Okay.
With the Markdown documents. And we were using, because we were doing remote, teaching, I was using the RStudio Cloud. So it worked actually really well.
Okay, good.
Yeah, thanks for writing this book. It's really useful.
Thank you.
So thank you for all these good questions and good discussions.